Hello everyone, welcome to AI Anytime channel. In this video, we are going to look at a hallucination evaluation model by Vectara. So Vectra is an LLM builder. Basically, it's a platform, and it's very famous for building LLM and also some of the RAG techniques that they created in the past. I also have a video on Vectra where we'll look at the hallucinations and how to build a better RAG. They have a technique called grounded generation technique, and that's where they got a bit of limelight. And now they are working on other techniques, and they have released an open source model here, guys, that's called hallucination evaluation model. It's a model based on Cross-Encoder. We'll talk about it when we go a bit into the video. But here, this video is going to be the part of our evaluation playlist. We have a playlist called evaluation of LLMs and RAGs, where we are exploring different techniques, models, frameworks, etc. to basically evaluate LLMs and your RAG techniques or the RAG based applications. Because the things are now getting serious, people are now focusing more on evaluations and building or better or optimized RAGs, how to do better measurement when it comes to evaluating matrices and all. And I think that's where we should look into it, because OpenAI is doing a lot of things, so you don't have to do the same thing that they are doing it. You should focus more on how to do it in a better way and more accurate way. And how do you find out? We have to first measure it, and that's where we are focusing. So if you look at here, it's a Hugging Face repository of Vectara, and they have a model called hallucination evaluation model. Okay, now very interestingly, because the model is based on Cross-Encoder. So if you look at here, it says Cross-Encoder for hallucination detection, and I have personally used Cross-Encoder a lot, and I will tell you that how this generative AI ecosystem is using Cross-Encoder. Now LangChain has something called long context reorder, where you do a re-ranking of your retrieved chunks. When you use a vector database, we retrieve the chunks. Basically, you can also re-rank them. And recently in OpenAI development day, OpenAI was showing their RAG journey, where they increased the accuracy of RAG, whatever they mean by the word accuracy, from 45% to 98%. And one of the most important features there was called re-ranking. So when you re-rank, and I have explained that in many of my previous videos, that LLM struggles with the middle context. And Stanford has a research paper called Lost in the Middle, where they explain that LLM basically ignores the middle chunks, the middle context. They look at the first context and the last context. And that's why you have to sometime re-rank your retriever, okay, the retrieved responses. And Cross-Encoder has been used to do that task. In many of the, like, Weaviate uses re-ranking, Coher has its own re-ranking methods. Most of them are originated from Cross-Encoder. It's all open source. You can use it. You can go to sentence transformers and you can do the re-ranking of your context. Now, coming back to this repository, if you look at here, it says the model was trained using Cross-Encoder class. So they have used the Cross-Encoder class to train a model, and we'll talk about the training data and how they have benchmarked it. And the model outputs a probability. So it's a probability value from 0 to 1, 0 being hallucination, okay, and 1 being factually consistent. So if your response, the score is more inclined towards 0, it means there are tendency of hallucination. Okay, now they have recommend a threshold value of 0.5. So if anything below 0.5, let's treat them as hallucination. That's what Vectra is recommending. Not I'm not recommending that. For the reason to create this video is that if you need an extra layer of validation, you can use this kind of techniques, but you cannot completely rely on it. But this is a very good validation layer that helps you do a preliminary validation of your RAG approaches or whatever you are building. Right now, let's look at the training data. It says this model is based on Microsoft dBERTA version 3. So they have used dBERTA version 3, and they have trained it further using Cross-Encoder class of sentence transformer. Natural language, you can see the data to determine textual entailment, because it's important. They are not looking at, and the good thing about Cross-Encoder is that it does not look at the sentence embeddings. Okay, it's both of your sentences go together, and there is a representation of both the sentences, and they learn like that. And we'll talk about it when we're writing the code. Now, if you look at here, it says before being further fine-tuned. So the pre-training happened with Debata v3 base. So they pre-trained the Debata v3 base on the data that they have, and they further fine-tuned on summarization data sets. Okay, and that's the reason, the context size that you have to look at is small right now. It's short. Uh, Data set with the samples annotated for factual consistency, including fever, vitamin C, and pause. You can look at the performances over here. They have, benchmarked it. So they have benchmarked on true data set where they get an AUC score. You can see of 0.872. This is very fascinating, looking like a traditional machine learning journey. But this is what it is. We have to focus on these things. Now there are three performance benchmarks that you can look at for hallucination. One is any scale, very famous. Then we have SAMAC benchmark, and then you have true data sets. Now it has been benchmarked on this, and they have a GitHub repository where they show a table. Now if you look at the table here, it shows all the famous LLMs, both open source and closed source models. You can look at a GPT-4, which has an hallucination rate of 3%. It makes sense also, right? Now, this is a very good exercise from an experimentation standpoint. If you are trying to recommend anything to your client, maybe this can help. Now you can look into this table and weave your story around it. Now, if you look at Llama 213b, have around 6% of hallucination rates. Google Palm, which is expected, because I have worked with Google Palm and I really don't like this model, to be honest. And you can see the hallucination rate over here. It's by 12.1% and 27.2% as well. And this is what it is. By the way, we have to work with it. Now, if you read the about, it's a leaderboard comparing LLM performance at producing hallucination when summarizing short documents. So right now, the recommendation is that you use it as an extra layer of validation. Now imagine if you build a application where there will be an input box, user will come and put their query, and then you first do a semantic search in your RAG approach. You retrieve from a vector database, and then you feed that relevant chunks to an LLM, and then LLM generates a response. Now what you can do, you can take that generated LLM response and then compare that with the context using this particular model, and that's what I'm going to show you in this video. So let's start our coding journey here, guys. Enough of the document and theory. You can read it on the Hugging Face and GitHub. I'll give the link in the description. Now let me open my evaluation folder. I'm just gonna copy this. Let me just copy, and I think I already have opened, so I'll just do a Jupyter notebook thingy here. So let me just do a Jupyter notebook. I'm gonna open my notebook. Now there are two ways you can use this model. Let me just create a notebook first, a Python 3 notebook. You can use this model through sentence transformer class, and you can also do it through transformers. If you don't want to use sentence transformer, but that's a recommended way. But you can also use it through transformer if you don't want a lot of dependencies in your code base. Let me just change the name here and call it hallucination. By the way, guys, hallucination is a complex topic. There will be a bit of hallucination, at least for, I don't know, for the next few months or year, I don't know. So let's get it from sentence transformers, and I'm just going to import Cross-Encoder. I don't know why it's not suggesting me, but anyway, Cross-Encoder. Now I'll show you Cross-Encoder first. Let me just open. Cross-Encoder is very famous, and sentence transformer also has something called by-encoder, and you can read those about sentence transformer thingy. Maybe you can read it over here. Now if you open Cross-Encoders, you can see it gives a comparison between by-encoder versus cross-encoder. In natural language earlier when we were working with BERT, etc., we used to do a lot of these things, right? So by-encoder focuses on cosine similarity. You can find it over here. And the cross-encoder, it says, if you look at the differences, by-encoders produce for a given sentence a sentence embedding. So it creates the embeddings for each the sentences. And then it's passed to a BERT independently the sentences A and B. Now if you have two sentences, which results in the sentence embeddings U and V, and then this sentence embeddings can be compared using a similarity algorithm like cosine, Jaccard, Levenstein, etc., etc., right? You can use anything you want. Now you can look at over here in the left hand side the by-encoder thingy. Now in the cross-encoder, what happens? We pass both sentences simultaneously, and there's a representation to the transformer network. So it can learn from it. It produces an output value between 0 and 1, indicating the similarity of the input sentence pair. It does not produce sentence embeddings, which has both pros and cons. We'll not go deep into it now. If you want to scale, right, if you want to build a scalable solution, and if you want to use this as a metric or a framework, rather not a metric, a framework to evaluate, I will not recommend it, because you cannot scale with this, right? Because it has a less context window that you can pass as a context to measure it, but it can act as an stand-alone validation layer. You can pass your retrieved chunk, and then the LLM responds to measure it each time in your application. That's how it can work, by the way. Now you can read about this. I'll give the link in description of all of this reading materials. Let's head back to our notebook, and in the notebook, let's get the model. So model equals, I'm going to use Cross-Encoder class, and in Cross-Encoder class, let me just get their repository name from here, and here I'm just going to pass it. So let me just pass this here, and what it will do, it will fetch the model for me, and that will be stored in your cache runtime or wherever you are working, right? Depends on what environment you are in. Now if I just do a model, you can see the model object. You can find the model object over here. Now we have loaded the model. For the first time, if you are doing it, it will take a bit of time. It will download around 800 MB of files altogether with the tokenizer, configs, model weights, etc., etc. Now we have loaded the model, guys. Let's create some let's have a variable called scores, the same, and then model.predict. So in model.predict, now it's a function, and inside this function I'm going to have a Python list, and inside the list we'll start our comparison thing. Okay, now in the Python list, it's a list of list that you pass. It's a list of list, and then you do a string inside the list, and there's a single string. You just do a comma that you separate with. I'll show you how. Now imagine if this is your retrieved chunk. Okay, one of the chunk, I'll say, okay, a man walks into a bar and buys a drink. Now imagine if this is your retrieved chunk from a vector database. That's the context, and then I'll just say this is your LLM response. A bloke swings alcohol at a pub. I misspelled it. Alcohol at a pub. Now imagine if this is your first one on the left hand side before the comma is your retrieved chunk, and the right hand side is LLM response. Now if I just do any I'll just run it here. Now once I run it, I can just do a scores, and you can find out the value of it's an array that it gives you. It says okay 0.61, and if you read the when I mentioned in the beginning of this hallucination evaluation model that it gives you a probability value between 0 and 1, and if anything less than 0.5 it means it's hallucinating. Okay, now the only concern I have is it's still doing a contextual similarity, which is good in a way. It's trying to understand the contextual meaning behind both the sentences, and then trying to come up with a value that says it's an hallucination. But hallucination can be of different types, in the complex situation. Let's see it out, guys. Now what I'll do here, I'll just copy this again here. I'll just come here, I'll say scores. Let's overwrite it. Okay, so let me just do here score thingy. I'll keep this, and I'll just copy a few of the things here. I'll say two. Okay, what happened? I'll just take a 5 or 6 examples here. Let me just do that. Okay, this looks nice. Now let's start changing it. Let's say, okay. Mm, 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 mm. Uh, uh, uh. A senior age person who drives once in a week. No, let me put it like this. A person who drives once in a week can be treated as a senior age person. Okay, now I'll just say senior person is someone goes uh, who goes grocery shopping once in a week. Okay, that's the one. Now let me just do. Okay, I forgot to give a comma or what. Okay, let's do that. Now this being one. Now let's change this. Mm, I like to eat apple as this is my favorite. This is my fav fruit or something like this. Okay, let's see that. And here you can write I don't like to eat apple as this is not my favorite fruit. Let's remove this three. Let's check for this three, guys. So what I've done here, I've created three sets now. And if you look at these three sets, the Python list, it's a list of list containing a string separated by a comma. Now the left hand side is your retrieved chunk and the right hand side is an LLM response. And you can just use this as a function and let's have an evaluation method. Now here, let's run it. It says, okay, I've given a two. Uh, anyway, let's remove this and see. Okay, I don't know why I can't find it. Now, if I just do any scores thingy here, let's see what we get. And it's okay, you cannot read it. So let's make it more interpretable. Okay, so you cannot interpret it. So what I'm going to do is import numpy as np. Let's quickly change something here. Let me just go up, add a few cells, and I'm just going to say scores one decimal or something. Let's do that. Okay, scores one decimal. I'm just going to do np dot around, and np dot around I'm going to pass scores, which is my variable, and I'm just going to do decimals here. So decimals one, let's see. And once I'm just going to do print scores one decimal, and you can find it out over here, right? uh, Interesting. Oh wow, you can see here it's not only the similarity of the keyword similarity or something like that, right? What I'm trying to show you, I'll make it bigger so you can just see it here. Okay, let me just make it bigger. Now if you look at the score that we got around 000, right, for this thing. And that's just surprising. It's not only the search, like a keyword similarity search or a keyword search, it understands the contextual meaning. And that's what I was talking about, the cross encoder class. If you look at the cross encoder of sentence transformers, it does not create sentence embedding for each sentences, but rather it's just fit it to a transformer network, and that it just gives you a probability value. So works good, I mean, on smaller or sort of shorter sentences, and that's what Vectra also is recommending right now. But this looks promising to me. I still have to evaluate this on a RAG, end-to-end RAG approaches. Maybe there can be a follow-up video, or if you can extend this further and let me know in the comment box, that also will be helpful, because now it excites me when I see this. It has a better understanding of the context of both the sentences, the retrieved chunks and the LLM response, in just in case, as an example. And it really works good if you look at over here. And now what I'll just do is, let me make it more presentable and see. It's fine. Yeah, it's for me still, yeah, it's working fine, at least for the sort of sentences. And I think this is promising, and I will do a bit of more development from an experimentation standpoint on this, on the different RAG approaches, and then there can be a follow-up video. But this is what I wanted to show you guys in this video, that how you can use a very new, released, as always, a very updated tutorial on hallucination evaluation model by Vectra, that you can use it to evaluate your RAG approach, okay, using something really powerful At the same time, traditional, we have used cross-encoder in a lot of our earlier experimentation and projects when we were working with BERT a couple of years back, where there were not that much of hype of large language model before the era of chat GPT, right? And this works really good. And the notebook will be available on the GitHub repository. I'll give the link in the description. This is part of my evaluation video series. Please follow that evaluation series because I recommend that your focus should now be on evaluating and benchmarking and measuring this racks and LMs, through different techniques. That's how you will be able to build better and optimized applications based on LLM, because then you'll find out where the real problem is. So I have created a video using Giscard. Last video, if you look at Giscard, which is a very powerful tool that also gives you the tendency of hallucinations, performance, scalability, over smartness, etc., etc. Now, uh, that's all, for this video, guys. If you have any question, thoughts, or feedbacks, please let me know. And if you haven't subscribed the channel yet, please do subscribe the channel. And if you like this video, hit the like icon and share the video and channel with your friends and to peer. Thank you so much for watching. See you in the next one.